Yes. So indeed, today we have this topic of machine learning, and let's look a little bit how the machine learning is used for processing data. In a traditional way, we have data, and then we make some let's look at here on the right hand side. So in the traditional way is that we have data that we feed into some algorithm, and then we have some algorithm that is going to some rules that are used by this algorithm, and the data is used by the algorithm, and it gives us answers. For example, we can program something simple like that if the light outside is too dim, and there is somebody moving on the yard, switch on the lights, and then these kind of things. So simple rules which are programmed. They can be also more complex, but this kind of thing. So this is like based on the human intelligence, human learning. Human knows how to what to do in certain conditions, and he or she will make the program to do it. And then you give the data, and you give use these rules, and then you got some actions or something. Decide what to do in this kind of conditions. And it can be also an algorithm that can read data and predict something, predict the tomorrow's weather, or classify bad potatoes from good potatoes, or in an automation system or whatever, or keep the car on the road. But that is all already pretty complex. So if you would think that how a human, what kind of program you would make to read all the sensors in the car, GPS, LiDAR, video camera, and everything, and make some algorithm that keeps the car driving on a good road, that would be pretty complex algorithm. And it's too slow process to do that in this kind of programming way, to transfer the human knowledge to a computer by programming. So what if instead we could just help the computer to learn these algorithms by themselves? And this is exactly what machine learning is about. So if we know that in these kind of conditions, that we have some data in this supervised learning case, we have some data, and then also there is some human expert or some other expert that is able to provide the correct answers. That in this kind of situation, when you are trying to keep this car in the road, you should turn slightly left. And then the computer, it has all these data, and it knows what is the current action in this case. It can learn the rules, how this data is transferred to actions. And then when you know these rules, then you can implement this algorithm that you just copy these rules into this programming part. You put the data in, it will use these rules and provide correct answers. That is kind of copying the actions made by this human reference player there. And this is now called supervised learning, because there is a supervisor, and it is this human expert in this case who knows what is supposed to be done in different kind of conditions, because he or she has been driving a car like 20 years. He knows what to do in different kind of situations. And this computer system is collecting the data and copying these actions that this supervisor is doing, and learning the rules, how these actions could have been actually decided based on the data only. And then when this is ready, then we can throw away the supervisor and let this computer to do these actions by itself. It is like I have two boys, and I have teach them to drive the car, and it's a little bit similar. that I'm sitting down on the right hand side. I have a brake pedal, and then I can just give instructions to this new driver, and he is then trying to learn how to drive a car. I give instructions, and I can also, in emergency situations, press the brake pedal, and then he will learn, and then he will become an independent driver. It's the same that here we can teach a computer to become an independent driver. And this is because these systems are too complex, and they cannot be every situation cannot be programmed by a human expert. But human expertise can be added there. So some parts of these, maybe pre-processing part or some other parts can be programmed by a human and then combined with this supervised learning system. And then you have a hybrid system, and that's maybe quite reasonable in many situations. But then there are also cases then you don't have this expert. And that is, of course, difficult. So what can be done in these kind of cases? Then we are talking about unsupervised learning. And unsupervised learning is that you only have data. And what you can do with only having the data, at least you can do some sort of clustering. And that means that you separate the data which is distributed maybe in unevenly in a space, so that there are dense regions and then sparse regions, and then you can consider that maybe there is a cluster there is some cluster, there is some cluster, and then there are empty areas in between, and then you have learned something from the data. And then you can name that, let's say that this is cluster 1, this is cluster 2, and this is cluster 3, and then you can, for example, calculate the averages of all these clusters, and you learn something from it. But of course, it's not yet ready, very useful when you don't know what these clusters are. But when you have done this, now you can start analyzing what is the content of this cluster 1. And then you will maybe recognize that, hey, these are apples. And then you can give a name for this cluster and say that, yes, these were apples. And it may, in many cases, help you to browse the data. And then also, in many cases, the data is very high dimensional. Here it was only 2 dimensional, so I have maybe only 2 variables, x1 and x2. And this is then simple to plot and analyze, but sometimes you may have high dimensional data, 100 dimensions or something, and then you cannot visualize it easily. So one very famous also unsupervised method is called subspace projection methods, like principal component analysis, that helps you to project this data in the lower dimensional space, for example, 2-dimensional space, and then you can plot this high dimensional space in 2-dimensional space. Of course, then some part of the information is lost, but it can be optimized so that the losses are minimal. And still, you will it can help you to understand the structure of the data better. And the reason, of course, that why we want to, in this supervised learning method, why we want to get rid of this supervisor is, of course, that the supervisor, that can be, for example, a human person, can be quite expensive. And then we can replace that with a computer by using machine learning, and then it is much cheaper. For example, in our case, we had recorded sound recordings nearby wind turbines over a year for 4 different locations. And then we wanted to analyze that what kind of noise sources, what kind of noise events there are. And I could do that manually, but that would require like 4 human years if provided that these persons would have been listening to data all day long. So in practice, it would be like 12 human years. But we were able to do that with machine learning in in few days. So therefore, machine learning is useful instead of using this expensive reference methods. And this is one. And one other reason is that, for example, chemical analysis, if we do like this traditional wet chemistry, it's slow and expensive. And then we can replace that with some optical spectroscopy measurements and machine learning, and it will be fast and cheap. All right, and these machine learning methods are used in surprisingly many sectors of life at the moment. This is 2 years ago, or actually 1 year ago. Then there is the Finnish baseball team, Kirittäret, who win the Finnish championship, and they say that they analyzed data more than other teams, and that was one of the reasons why they won. And I think in this level, the skills of all the teams are really high, and maybe not there is not so much difference. So then, if you have some other advantages, it can easily make the difference here. And they won. But actually, this year they were only the second, and it was other team from, was it Pori, who won. So maybe they have also started using machine learning for their teams. They didn't say, I don't know, but it's also important in sports, in football, in this ski jumping. It's really important to analyze every jump. When what was the timing? What was the strength of the and what was the speed, and everything like this. And easily you will get, with all those sensors, you have so much data that it's really difficult to try to figure out what data is important, how to use this data. But with machine learning, you can more easily understand and be able to utilize all this data. And at the moment, we have so much data. When people go to shopping, they buy different things, they walk different areas on the shop, and they visit different shops, they visit web shops, and all this information is collected. And also then people are asking that what to do with all this data, can we learn something from it? And then they are want to try different machine learning methods to be able to utilize all these big data sources. So simply, we have too much data to be analyzed by human beings at the moment. But if you utilize computers in a smart way, we can learn plenty from that data. And it can have big effects in business, in politics. Politics is very important and interesting area. When the USA elections, there was a lot of discussion about a company called Cambridge Analytica. And they were using data from Facebook and different sources, and they analyzed kind of social networks, that what kind of people are discussing and which kind of topics they are discussing, how they are connected to each other, what are they angry about. You can do from the written text, you can do so-called sentiment analysis, so that you can analyze that were those people happy or angry, or what was the emotion when they were writing these texts, and to whom they were publishing it, with whom they are working with. And then you can identify networks, you can identify people who are kind of opinion leaders on these networks, who are connecting different networks to each other. And if you want to affect these people, which kind of message do you need to feed to which people? And these are the social networks are kind of enormous source of information that can help to learn how we people are connected to each other, what we like and what we hate. And if you want to create reactions, you can optimize these reactions based on data analytics. And I think that this was done in USA elections, but also I think in many other elections and Brexit voting and many kind of effects. And I think that we are all prone to these kind of attempts every day. So that's also why we need to be aware of machine learning and all kind of these attempts to affect us. And there is in our eastern neighbor, they have the country in the east, they have different sections of people who are doing this kind of trying to affect our opinions through the social media. And this Internet Research Agency is a Russian institute who is doing this kind of work as well. They are analyzing social networks and then they are affecting us. And sometimes it has been wondered that what is the business case of Facebook? Where do they get their money? Why it exists? And what is the product? And there was some it was mentioned in this Valvontakapitalismin vaarat or Social Dilemma movie that if you wonder that what is the product of this company and you don't know what the product is, it's probably you who is the product. And they claim that in Facebook and a social network, it's the users who are the products. And it is a misconception that we think that they are selling our kind of browsing information or these kind of things are the user data to other companies. But actually, they are selling the other companies the methods how to affect us. That if you want to affect people, change their opinions, you can ask from these companies, what should I do? What kind of message to whom I need to give to be able to affect them? That was what they said in this film. It can be true, I don't know, but at least you need machine learning for doing this, and you need to understand machine learning to be able to understand that this is actually possible scenario. And this is, we know that machine learning has been very important part for this kind of political and business side to understand people and try to maximize the effort, what they do. And then starting from the simple things in machine learning, one of the most famous and well-known topic is regression. The term regression is misleading. It was used because there was a person who was analyzing the length of the school kids, and he noticed that the length has been rising, and it was every year a little bit higher and higher, and he tried to predict that, and then he noticed that at a certain time the race was stopping and kind of regressed. And then he published scientific articles about this, and this method became very popular, and others were using that also. And they were all talking about this regression, so it is quite a misleading term. So this is, but it is always used also today. So let's call it regression then. But the idea is that we have some observations. So we have some samples somewhere, and then we want to build a model that how to predict the y based on x. And if your data happens to be kind of there seems to be a linear dependency, then you can make a simple model by drawing a line from here to here, and then this line is the model of how to predict y from x. And it's mainly true. There is some disturbances, some deviations from this model, but mainly the idea is correct, and this is called linear regression. And now we have, and this actually is now that y is predicted from x using some function f. And now this function is some, we can see here that it's actually something, some coefficient times x. So this is really linear regression, and often in regression, this coefficient is called as beta. So this would be a simple linear model of this. And for example, in this case, that we have the y is these values and x is these values. Another question is that so these values that we have are kind of used for teaching. So learning this model, and then there is one value that we don't know, and we can use this model for predicting that value. And here we can now think that what is the model to predicting this. And quite easily we can see that, okay, when x is 0, y is 0, so it's here. When x is 1, y is 2. So it's quite obvious that this model is actually that y equals to 2 times x. So this is always doubled. So then this value here must be 8. So this was really simple regression model. But this is of course overly simplistic, and normally today it doesn't look like this, but it's more like this. So this is actually exactly the same model, but now we have some noise in this. So therefore, there is no exact match for the model, and we cannot exactly predict this. But therefore, we try to, so the situation is similar than here. In this example data, all these values were exactly in this line, but now in this case, they are not in this line, but somewhere near around. So we need to kind of build the model that best matches into this data, and none of them do exactly match. And this is exactly how the problem that the regression can solve. It can use it will minimize the error of between the model and the true and the data in least mean square sense, and therefore it is called least mean square regression. And then also we can have, now I can't draw anymore, I have to reload this. There seems to be some problem with the techniques, not a surprise. So in this case, we have few variables. So we are not trying to predict y only from one variable, but several variables. So it's the problem is like this. So now it is not that simple anymore, but the same algorithm works, and we can pretty easily solve the missing value here. There is mathematics behind this, but we can use it simply by using some Python code, as I'm going to show here on the next. And before going there, we need to also discuss a little bit about the how to evaluate the quality of the model. So what if we have data that is somehow here distributed, and we try to predict it based on this model? So how good is this model? How can we measure the quality of it? And one of the most famous is this coefficient of determination that is called R squared. And this is actually defined in this way. So it is the when this data here is distributed in okay, this is variance of y, of course. So variance kind of describes that how much variability is in the data. So how much this data is distributed in y-axis. And then we try to predict that based on this model. And then we calculate the prediction error, that is the true value of y minus the predicted value of y, and that squared. This is the variance of the prediction error, and then under the line we have the variance of y, so it is y minus its mean value. This was supposed to be hat. So this is the predicted value of y, this is the mean value of y. So this is the normal variance, and this is the variance what is remaining when we predict. And if this prediction is perfect, so we always exactly predict the y value, then this will be 0. So we have 0 here on the up side of this, and there is something in 0 divided by something, it will be 0. So 1 minus 0 is 1. So r squared is 1. So the perfect fit will mean that r squared is 1. And if we have, if we totally fail to predict, and there is still, then what happens is that this y is actually the variance of this is equal to variance of this. This is, by the way, squared as well. And that means that this will be 1, and 1 minus 1 is 0, so r squared will be 0. So this is a value that is scaled between 0 and 1, and 0 means that this model does not fit to the data, it doesn't help at all, and 1 means that it fits perfectly. And then we have also root mean square error, that is that prediction that means that it's the root of the mean of square. Oh, doesn't look very good. But anyway, it's the difference of the actual value and the predicted value that's squared. We sum all of these values. So because we have error here, we have error here, we have here and here and here, and we sum them all together and squared, and then divide the number of these errors, that is the mean squared error, and then we calculate the square root of that, and that is the root mean square error. And these two measures are the most useful for measuring the fitness of the model. Okay, so now we try to apply this regression method and calculate its fitness. There is first some code that we need to just initialize this, and you don't need to worry about this if you don't want to. And then we go to this, there is plenty of code to make this interactive model work, and you don't need to worry about that code, but let's look at this in the interactive plot. So this is showing that now we are first generating the data, and we have some process model. So it's something that we feed in some value of x, and then there is some value of y coming out. And in this case, the y is a times x squared plus b times x plus c plus some noise. And now we can adjust all these values. So for example, I can put the noise to 0, and I can put this a to 0. 0 was not there. And then this is a line because a is 0, it's only bx plus c. And it will be a line, and I can adjust the angle. Let's put it like 1. And it's only, you can only see that the y-axis is scaled, or 1.1, something like this. And then you can change the zero crossing, whatever you like. Let's put 0.4. And then we can also make this a little bit nonlinear by adding some coefficient for a, and then put some data, some noise in the data. So this could be now some process that we want to model. And of course, when this a is not 0, this is not linear, and that means that the linear regression is not perfectly fitting into this. But let's try this anyway. So now we have data, and now we try to fit the linear model into this. And here is now the data that we generated on the last page. Now I can try to fit this line into this by adjusting the angle and the zero crossing position. And here it's very small, but here in the end you can see the coefficient of fitness, so r squared there. So I can try to maximize it. And if I put this very wrong, this can be even negative. So it was increasing the variance, so this model is making the situation worse. But if I make it pretty good, then I can have it close to 0.85. And this may be the best I can do. No. But yeah, something like this. So now I have found that this model, that y is 2.4 times x minus 2 fits to this data very well. And in regression terms, I would say that this is beta 1 times x plus beta 0, and beta 1 would be 2.4, and beta 0 would be minus 2. So this is one simple way of machine learning, and there are many other methods in a toolbox, many nonlinear, multidimensional, and this kind of stuff, and they are able to predict much more complex data in much more difficult situations. And then when we have the model, we can predict the values. So now we can predict the values that were missing. So we had the data that this is actually predicting this data that you saw graphically. So the true model would say that if x is 0, the y should be 0.4, and our predictive was 0.0. So this was slightly not correct. There was some amount of error in it. Then we can calculate the squared error. and absolute error. That is also one measure for the fitness. And then we repeat this for all of these points, 1, 2, 3, 4, and they all have some prediction error. We can square it and sum it and calculate the square. So the square mean, the root mean square error is 1.27. And mean absolute error would be 1.16. And R squared, you already saw, it was 0.85. So in this way, we can make the model, use it for prediction, and also then estimate, measure the quality of the model. Any questions about this?
So in the practice, after we measure all this.
Yes, okay, maybe I have been progressing a little bit slow. So let's go slightly faster. So in general case, the question about supervised machine learning is like this, that we have plenty of data in that we have collected, and then we try to build a function that can predict some of the something based on this data. And in this case, when we had this linear regression, we had only one variable. It was only x1 kind of, so it was this kind of one column. Then we had many dots. So we had one point like x is 0, it was here, and then we knew that the correct value for y, it was here, the corresponding value. And the same for all of this. So these are like the samples are here on this rows. And then we have the variables here. And in this case that I showed, we had only one variable, and then we had the function that was a linear prediction, and we predicted these values of y. And when we knew some of them already, we were able to optimize this function, and then we can apply it to the new data that we haven't seen yet. But in a general case, there can be much more variables here, so many other columns in this matrix. And and therefore this function can be like y is beta 1 times x1 plus beta 2 times x2 plus beta 3 times x3 plus some beta 0, that is zeta crossing, and therefore we would use linear model to predict from more data these values. Okay, there is some more information in it and how it is actually solved in mathematics. So basically, it only needs matrix multiplications and inversions, and it can be calculated in so-called closed form. So you don't need to iteratively solve it, but just one kind of matrix set of matrix operations, and therefore we can say that it is fast. So you can, and it is also easy because it is well defined, and it's implemented in many software packages as well. So you can easily calculate this. It's always available. And by the way, this X is called as a design matrix when it is organized like this, and you have all this data there. And now let's go some examples of this. And this is the heating power versus temperature. So we believe that that when the temperature goes, there is like 0, or let's put 0 there where it should be. That if temperature is like -40 to +40, that when it is colder, you probably need more power for heating the house or other premises. And when you go near to, and in plus 40, you don't need heating at all. Maybe there in plus 10, you already need a little bit, and then it is somehow increasing the heat need when the temperature rises. But we don't know the model, and we actually do not know if this is a linear relationship, but let's see from the data. And in this case, I have data. It's actually from Sodankylä. And we have also some other weather parameters. So it may be that also something else is affecting to this model. So in this data set here, it contains true measurements from Sodankylä municipality. And this is the heating power in megawatts, I think, that what is needed for heat in the central heating system of Sodankylä. And this is the temperature here. Then also I have collected some other weather information because I was thinking that maybe wind is also affecting to this heat need, maybe rain and cloudiness. So I collected this data and start analyze what does it mean? Can we predict the heat need based on the weather information? And when starting to do this kind of analysis, it's and when you don't know much yet about the data, it's good to explore this data a little bit. And one very nice way to study correlation and regression is this, to plot this kind of scatter plots and study them visually. I use this magnificent Seaborn library that is able to make very nice statistical plots. You can see all these source code from this notebook. You can run it yourself and use the code in your solutions if you want. And what you now see in this graph is that I have here one of these variables, that is the heat need, how much heating was needed. In this column there is the histogram of this data. So I will notice that quite often there is no heat need or its heat need is very little. In this moderate heat need is also quite often happening, but these very large heat needs are quite rare. So this is the histogram of the heat needs. And then on the next column, I have the heat need against the temperature. And it seems that indeed, when temperature is minus 25, we have heat need something like 20 megawatts. And then when we have temperatures 25, it's only a few megawatts. And it seems that this dependency is indeed quite linear. And then we can really analyze that. We will maybe know that this is actually governed by so-called Fourier law, and it is indeed should be linear. But then there is some nonlinearity in the end. So it seems that we always need certain amount of heat. But the linear model could explain quite a lot of this dependency already. Then we can study the wind speed and how that is affecting the heat. That is seemingly not that clear. Maybe when the wind is high, it almost seems like the heat need is less. And when the wind is a little, then there is a more heat need, and that may be a little bit counterintuitive. But then when we look this column here, we will notice that temperature and wind speed are correlated. In a very cold temperature, there is less wind. So therefore, in this way, these are connected, and not in that way that higher wind speed would reduce. So there is no cause and effect relationship between them possibly, but more like that these parameters are mutually correlated, and that's often slightly difficult. And then there's also rain. It's a little bit like maybe not that interesting. It seems that that the rain is more dependent also on temperature, so it's difficult to see how useful these are. But at least we can already say that temperature is important, and these others maybe, but they are not maybe. Probably they are not that important. So let's then make the model, and here it's done. So I only take from sklearn library. It is the code is there was slightly earlier, the so-called linear regression class, and I implement a linear regression object based on that. And then when I have now this model, I will fit it to the data. So this may be not that easily readable, but this is the X data, and this is the Y data. So I trained the model, used what I already know about X and Y. And then I can, and then this is it. Now the model is built based on these observations. And then I can calculate there, I can read from the model that what was the regression coefficient, beta 1, and what was the intercept, beta 0. And then I believe that my model is beta 0 plus beta 1 times X, and X is now the temperature, and Y is the heating power needed. And then I am plotting first the data. So this data is now the measurements, what I have read from the Sodankylä municipality. It is in so-called data frame object, and it's very easy to plot that data frame object. I say that plot a scatter plot where in x-axis I put the temperature, and in y-axis I put the heat. And then I can adjust a little bit that use only small, the size of these dots in the plot will be very small, only 2, and they are slightly transparent, and the color will be blue. And then I also plot this model. So I plot a line where in the x-axis I have the temperature, and in y-axis I have this model over here. So B0 plus B1 times data temperature, and I plot it in red color and no transparent at all. And then here it is. So we have the data is in blue dots, and the model is in red line. So now it is fitted, and we can now predict this heating power based on the temperature. And there is, of course, certain variance around this line. So model is not fitting perfectly, but it's fitting pretty good. But then there is a considerable discrepancy in this region, and here maybe I would need to have a different model when the temperature is here above plus 15. It seems that this data is that there is always need for heat even in summertime, and that makes sense because also people need hot water. And then I also plotted this model in here. So we know now that the temperature, the heating need is minus 0.36 times temperature plus 8.4 megawatts. So at temperature is 0 here, then we need 8.4 megawatts of power. And the fit is pretty good. it's 0.94. And then we can, for example, predict based on this model. I don't need to do this manually like I have done it here to actually build this model, because it's already inside this reg object, and I can easily use it like this, that I predict the energy consumption when the temperature is -10, and then it says that it's 11.99 megawatts. So -10, 11.55. So now, and actually this is what we made a simulator that tries to simulate and optimize the energy production and consumption in Sodankylä, and I replaced this measurement with this model. So I built this model, and when I wanted to predict the energy consumption in Sodankylä at a certain day, I just used the FMI data to measure the temperature, and then I used this model to predict the energy consumption, and that made the system much more simpler. I can also predict when we had this model from a certain year, I think it was 2016, then I can apply it to some other years as well. And I know that what is the energy consumption in 2020 January, for example, because I can now use this model instead of actual measurements. Because measurements are quite expensive and they are hard to get. So this is one case how to use this. And I also try to add there the cloudness data and wind speed and try them, but I noticed that my coefficient of fitness was not so much improved. So then I concluded that it's the temperature that is the best to use in this model, and these other parameters are not improving it significantly, so I left them out. But even it is quite obvious by looking at that scatter plots already, but it's still good to build the actual model and see that are they useful or not. And in this case, we know that the underlying phenomenon is linear, so linear regression is optimal here. But in some other cases, it may not be linear, and there can be other issues, and then we need to use other regression models. But for example, in this library called sklearn that I use in Python, there are a huge number of different regression methods. Some of them are also directly applicable for high-dimensional data, and therefore and nonlinear, so they are much more general than this linear model. Then we can, then I was going to stop the regression part here and start talking about classification, but any questions related to this regression? Okay, well, let's continue to the classification part. And this is one of the most famous data sets related to classification. It's this IRIS data set that is collected by Fisher. And here you see IRIS flowers with three different species. We have Setosa, versicolor, and virginica. And the question is that if we measure certain features based on these flowers, can we recognize these different species based on these features? And the features that are selected are the width and height of certain leaves of these flowers. To be more specific, the petals, which are here marked as red. So these petals or these sepals. All of these flowers have these petals and sepals, and they are slightly different shape. So are they good for recognizing these flowers. And why this could be interesting, that some flower expert probably recognizes these species based on many other information, and they can provide us sample data so that they will measure these sepal and petal widths and heights and put them on the table, and then they will also write there what was the correct species of this flower. And then we try to use the machine learning algorithm to build a model which can predict this species based on these measurements. And then when that is ready, then someone who is not an expert can go and just make these same measurements, and the system can predict the species of that flower. And this is the general concept of classification, and it can be applied to tons of different applications, include classification of people in the social network, for example, which are Republicans and which are Democrats. But let's look at this flower example further. So here is all the code that is needed for it, so you can go through it and repeat it by yourself. But in this sklearn, that is a very famous machine learning package in Python, I have just imported something called datasets, and this includes so many datasets that can be used for testing different machine learning algorithms. So one of the datasets is this IRIS dataset. Then I also import some classifier called SVM, that is support vector machine. That is one famous and quite general classification algorithm. And then from these datasets, I'm loading this IRIS dataset that I can use. And then I have some couple of my own functions that I have implemented in a library called snippets. It's also included in the GitHub. You can take a look what this plotdb and display support vectors means. And then I import a couple of metrics, accuracy score and confusion matrix, to analyze the accuracy of this classifier. So they are similar than R-squared score was for regression, but here we talk more about accuracy of the classifier. So let's load the data set and study that a little bit. So this is some sample. I have read the data in again a pandas data frame. That is one data structure that contains data. It also includes many of the statistical processing functions that are useful. So it's very good for data analysis. And first of all, I sample 5 rows, randomly select 5 rows from the data. And I will see that that here I have, these are just the numbers, the row number from the data set. So these are really random samples that I have took. And all of these samples have one feature, that is a sepal length, sepal width, petal length, and petal width. And there are some values, so 6.4 centimeters to 3.2 centimeters and so on. And then the species is now just described here as an integer, 1, 0, or 2. And I have also printed here the target names. So these names. So I know that the 0 means now Setosa, 1 is versicolor, and 2 is Virginica. So here I have some sample data. And then I have also plotted it here. And I plotted it so that I have a scatter plot. So I plotted 2 of these variables, because this is now 4-dimensional data. I have 4 different features. I cannot plot them all. So I selected only 2. So I selected all rows and column number 0. So here is the sepal length. And then I plotted all rows, but the column number 2, that is the petal length. And here they are. Sepal length is in the x-axis, petal length in the y-axis, and I can already see that indeed, based on these variables, it seems that these guys here are can be distinguished from these other flowers, but these two are more mixed together. And but if I add two more variables, this sepal length 1 and petal length 3, maybe then this works better. But I cannot visualize it easily in two-dimensional space. So let's try to build a classifier and try to classify these three different species. And now I used here the color in this drawing that is the target class. So therefore these are in three different colors, and I know that they are like different species. So I know the true classification, and now I just need to teach the computer to repeat the process. And that is easy. Here I have placed all these measurements in matrix X, and I only, oh actually yes, I only took like these two same columns, 0 and 2, because I wanted to be able to plot it easily. So I only selected two-dimensional scales. I could have put here all, but I only selected now 2 for the sake of simplicity. And I selected all the rows, all the samples. This is what it means. And then okay, this is slightly complicated because this is now interactive, but the actual classification happens here. So I already imported the support vector machine previously, and from that class, I now instantiate the support vector machine classifier using, it's using so-called kernels, and I use now a radial basis function that is some sort of kind of circular kernel. And then usually in these classifiers, I need to put certain parameters like C and gamma. And now you may wonder what this gamma is, but I can actually demonstrate it because it's here in this interactive plot. I can change this value of gamma and see how it works. And then when I have now specified which kind of classifier I want to use, then I need to train it. So I feed it to the data. I say that the data is in variable X. The true value, true classes are in this iris.target, and then it fits the predictor for this case. And then when it is fit, I can now predict these classes by using only the data X, and it will predict the classes. And then I also do some tricks in my specific code to be able to show these so-called decision boundaries on the plot. And then I also calculate the accuracy, that how accurate this classification was. And this is made by giving this accuracy score, the true classes and the predicted classes, and it will compare them and see how many of these classes were correct, how many percentage. And now let's us see. So this this graph here, some technical issues. Yeah, now it works. So now the gamma is very small, 0.01, and when this gamma is very small, it makes these decision boundaries to be very linear. And this decision boundary means that all the values which are, for example, in this red area, they are deemed to belong into this red class. And everything that is in this green area, they belong to this green class, and same for this bluish area. And now when I increase this gamma, I can change the parameters of this classifier. And what happens is that these decision boundaries become more complex. And when I put a very high value in this gamma, it's making it look like this. And now the accuracy score is 0.97. It is not actually plotting it. Update. Yeah, it is updating it, yes. So it's 0.90 now. So 90% of the values are correctly classified. Then I can increase, it's 995 now. I can further increase, it's 95. I can further increase, now it is 97. So which gamma value is optimal for classifying these different flowers? It may feel so that this gamma of 5 is optimal because now we can correctly separate 97% of these values. And this, for example, wouldn't be so good because now we can only separate or correctly classify 95% of the samples. But that is not that simple because if we go to very high value of gamma, now we have kind of a lot of complexity in these decision boundaries, and they are very small. So now for this data that we have now, this is the best value for gamma. But if we measure future values, more values for these different flowers, this red area is now pretty small. And what if we find out some flowers which I think I had to draw, but my drawing is not working, so I have to again reload this. So if we have this situation and we find more flowers, and what if we have flowers in this region? What is the most probable class for them? I suppose they would belong to this red class because they are clearly far from these others. But now, according to this classifier, they would be classified as blue class, and that's probably wrong. But if we put this a little bit kind of more flexible or more relaxed classifier, now it would be much more believable for this case. And also, if we find some other like green flowers here, they would still belong into this class, or more blue flowers. So if there is slightly more samples, slightly different, then where would they belong to? And now this would be seems pretty good, and this is maybe too narrow system. So we say that this is now indeed very good in this training set, in this data set, that what we have used for training it, but it may be so that this is not very good of predicting future values. So we say that this classifier is now overfitted to this data, and we need to relax it a little bit so that it can also predict the future values well. So we cannot only look at the current data, we need to also prepare for prediction of the future data. And therefore, this gamma needs to be selected carefully, and then we also need to use certain means to validate this model for future data. And it can be done in such a way that if I have the data here, I select part of this data for training the classifier, and then I spare some of the data, and when the classifier is ready, I try to predict this other part of the data that I call as testing data. And if I can get high accuracy also in this testing set, then I know that my classifier is probably good also predicting the future data. So it is not enough to only be able to predict the existing data, what we used for training, but it's actually more interesting to predict the future data, and we need to test for that. Otherwise, there is a danger of this overfitting. There is so many issues. I think we need to continue also on the next week, but now I would like to show you a tool called Orange. You can look at this material that I had, and there is all the code in Python. So if you need classification, regression, you can start from that material and start modifying the code for your needs. But then there is also another way. So, that is, you can do plenty of things also without programming, and that is actually quite interesting. So you can install this Orange tool, and now I have it here. I think I need to share the whole screen so that you can see everything. Can you see this Orange now? So this is a tool for machine learning without programming, so that can be attractive for many. But and it's actually quite useful for many purposes. This is an open source tool made on the University of Ljubljana. So I first start here by making a new experiment, and there are on the left hand side I have different panels where I have different tools. And now I start from the data panel, and I drag here a tool called File. And I double click it, and I will see there different, I can put here, browse a data file if I want to use some of them, but I can also use ready-made data sources. And now I select this iris.tab, and it already shows here that I have here a variable called sepal length, sepal width, pedal length, pedal width. They are numeric, they are features. And then there is also the target variable, which is categorical, and that is the species of this flower. So that sounds good. Then I can take this data table to visualize this data, and here I can just easily connect these together by tracking here this data to here. And now when I double click this data table, I will see the data, and there seems to be indeed plenty of different flowers. They have different sepal length and sepal widths. And now to repeat this classification process, I need to take from the supervised, from the model section, I need to take this support vector machine here, and here I place the data in it, and then I can double click and look at some of these parameters. And here we have also some parameters, and now I can, for example, use this radial basis function kernel or linear kernel, and I can adjust the G value, the gamma value, or I can use let it automatically adjust it. So I let it automatically adjust it. Yes. And then I just need to test that how good, train the model and test how good it works. And for that purpose, I need, where is it? Yeah, here. Test and score. I think it was this. And this can test this model, but I need to put here, like it says, the learner, but also the data. And now it uses this data to test this classifier. Now I can see that there is an support was support vector mapping classifier, and its precision is 0.96. So it was able to predict 96% of these flowers in a correct way. And this has actually used a technique called cross-validation to validate this model. So it's actually separating this data set in 5 different folds, and it is using 4 of them for training the classifier, and then it's predicting 1 which is not used during the training, and then it changes it 5 times until every fold has been used for both training and testing. And then it calculates the accuracy of prediction on that set that was not included in testing. So this is actually already a pretty good prediction of this accuracy on the new data. And then when we have all this there, we can easily add there more classifiers. Naive Bayes is one of the classifier. I just plug it in like this and like this. And then we can also take some random forest. I think this same object can be used for classifier and regressor. And then we can look the results. And it seems that naive Bayes has not been that good, but random forest and support vector classifier have been quite successful in this case. But there are some 4% of data that cannot be very well estimated. And we can also easily here visualize the data. We can put these same scatter plots in here. And now we see where the different flowers are. And now I have put here sepal length and sepal width. But in that Python code, I had here petal length. So I can also change the y-axis. And now it looks pretty much the same that I had in the material. Yes. So this is quite nice tool for doing many kinds of machine learning trials. And sometimes I use this to first explore the data and possibilities in it. And then only when I know what I do, then I will more like start making my Python code. Many of you were talking about Silhouette. No, it was actually a different course, yeah. But anyway, there are plenty of different tools, and this is a great way of learning these by experimenting them in this environment. And you can install this by if you have installed Anaconda Python. You can, from Anaconda Navigator, you just click this orange button, or you can download it from its web page, or you can install it in Linux by apt install orange or similar way. What we didn't cover today is neural networks, but I think we have to continue from here next week because neural networks are also really interesting stuff. And
Tomorrow we have your lecture also, I think.
yeah, in Friday we have one more lecture from my side, so we will tomorrow then discuss about neural networks.